Good morning, everyone. It's a good time to start with our colleagues at AIP. We have decided to launch this seminar series, AI for Science, and we have many good reasons to launch this. Mostly the recent rapid development of the movement for AI for Science, and so I'm very happy to uh, uh, have it realized here. Okay. My name is Naoki Yoshida, and I'm an AIP member leading a STAT astrophysics group. And our first speaker today is Professor Kana Moriwaki from University of Tokyo. She's also affiliated at AIP, and she will tell us about the fundamental physics and cosmology with machine learning and AI. We aim at about like 30 minutes talk and plus questions and answers. Okay, Professor Moriwaki, please.
Thank you. Thank you for introduction. So hello, nice to meet you. I'm Kana Moriwaki from Statistical Astrophysics team. So today I would like to introduce a few kind of use cases of machine learning techniques in our research field of cosmology and astrophysics. So let me start. Before going into the detailed use cases, because I think many of people here are studying a lot of different fields of research, I would like to introduce what is cosmology and what we are doing. So here is an image of the sky we can observe from the Earth. And you can see a kind of line here, which is the Milky Way galaxy we are living. So in our study, we focus on galaxy, but not the Milky Way. If you look at the very blank field, for example, somewhere like here or there, blank field in the sky, with a very good eye or good telescope, you can see a lot of very beautiful like object. And zooming in some of them, you can see a nice kind of spiral features like this. So these are all galaxies outside the Milky Way. Because they're very beauty, so it's really interesting in how they are formed and so on. But in cosmology, we only focus on the galaxy distribution. So if you have those galaxies, we only focus on the positions of them. So if you have this kind of images, we mark the position of this galaxy and put a dot here and so on. So we are interested in this kind of galaxy distribution. If we like point these galaxy positions on the sky, for example, this is the north sky, it looks like this. So one thing to know is that this blank region is actually the place we look at the Milky Way. So it's not that there is no external like galaxies outside the Milky Way, but because the Milky Way is too bright, we cannot see a lot of galaxies in this region. But outside this region, we can detect so many galaxies. However, this galaxy distribution on two-dimensional like sky doesn't tell us the actual three-dimensional galaxy distribution, which is actually what we really want to see. So to detect the galaxy position in the three-dimensional like space in the universe, we need to measure emission lines. To do that, we do a spectroscopic observation. So here is an example of a spectrum of a galaxy. The horizontal axis is the wavelength and the vertical axis is flux. Due to the cosmic expansion, so the universe is expanding, because of that, the emission lines, which has a very specific wavelength to be very bright, the emission lines from distant galaxies are like shifted toward the longer wavelengths. So, for example, in this case, the emission line of hydrogen gas, H alpha, which have a rest frame wavelength of this, is kind of redshifted toward, in this case, these wavelengths. So this is kind of a Doppler shift, and we call it a redshift because the wavelengths becomes longer. Because we know that more distant galaxies are more redshifted. We can, by just measuring where the specific emission lines are observed, we can know the distances of individual galaxies. So this is how we measure the three-dimensional position of galaxies in the universe. And here is an example of the distribution we measured with a kind of galaxy survey called 2DF, Galaxy Registry Survey. So we are here, and the galaxies are now known to be very distributed over a wide range of the universe. And some of you might notice that the galaxies are not randomly distributed, but rather that they form some kind of interesting feature of structure. For example, here is a cluster of galaxies. So I forgot one thing to note. The white point indicate a single galaxy. So here, white region is a cloud of galaxies. So there are some regions have less galaxies, some regions have more galaxies. So you can find a cluster of galaxies and also some filamentary structures formed by the cluster of galaxies. So this kind of structure is called the large-scale structure, and we are interested in how this kind of structure is formed. Using a simulation, we can actually follow the structure formation. We can kind of understand how the structure is formed in the long history of the universe. So here is a simulation output. I will start the simulation now. So from the very initial stage of the universe, the matter in the universe is attracting each other through a gravity, and they form a kind of very dense peak. So that the white point here is the dense peak. I will restart this. So at the very beginning of the universe, there are almost nothing, but as time passes, the matter is attracted each other, and they form a very interesting, large-scale structure in the universe that is very similar to what we observe in actual universe. So something like this and this. So actually, in the structure formation, there are two key elements. One is the initial condition. So depending on the initial condition, the final structure we observe will differ. And also the components of the universe actually also plays a crucial role in determining the structure. And actually, in addition to the well-known normal material baryon, we have the universe is composed of a lot of unknown matter called dark matter plus unknown energy source, dark energy. Inversely, because the structure is determined by these two key elements, we can understand the components of the universe and the initial condition of the universe by just measuring the large-scale galaxy distribution. As an example, here is two set of simulation output where we changed some cosmological parameters. So on the left, I show two panels showing two different dark matter setup. So the left one shows the structure formed in the universe where dark matter is kind of warm. Well, on the right, here is the structure formed in the universe where the dark matter is somewhat cold. So you can see the structure, the properties of the structure are quite different. Also here on the right, I show the two example of the simulation output where the components of the matter okay. This one includes dark energy, which causes expansion of the universe, while the right one doesn't have any dark energy and so doesn't experience any cosmic expansion. Again, there are some obvious differences between these two. The current observations are consistent with these two middle panels. So currently, our understanding is that the universe is composed of cold dark matter plus dark energy causing cosmic expansion. So this example shows we can actually get some information of our universe by just observing the structure, the large-scale structure, through galaxy observation. Then, today, I would like to introduce two use cases in the field of cosmology, use cases of machine learning in the field of cosmology. One is signal suppletion, and the other is mock generation. So let me first talk about signal suppletion. So although I have shown an example that the current observation have already provided us a lot of information on dark matter, the property of dark matter, and the proportion of dark energy in the total energy in the universe. There are several open questions to be answered. For example, we actually don't know the details of dark energy or dark matter. So we really want to know what is dark energy, dark matter. And also the initial condition, the actual mechanism that created the initial condition is not yet clear. Also, by observing large-scale structure, we can understand the neutrino mass, or we can also understand some kind of big event during the whole history of the universe, including the so-called cosmic reionization. To answer this kind of thing, it is very important to observe the very distant universe at the galaxies at very greater distances. This actually corresponds to looking into the very past universe. However, to observe galaxies at greater distances, there is a serious problem of signal confusion. So here is what we call lightocon. So let us think of this kind of cone in a specific region of the sky. If we want to measure distribution of galaxies at these distances, so the right is closer to us, the left is more distant from us. So if we want to observe galaxies at these distances, so it looks like this, for example. By the way, this is, for example, traced by the specific emission of oxygen gas. These galaxies emissions are always contaminated by galaxies at more closer galaxies to Earth. So in this case, H alpha emission, hydrogen emission from galaxies at these distances kind of contaminate to what we really want to observe. So what we actually observe is some kind of sum of these two emission signals. So although we want to know the distribution of galaxies like this, what we really observe is like the sum of them. So it doesn't tell anything real. Our proposal here is to use a machine learning technique to get to separate these two emission signals from only one single observation of this. Actually, so interestingly, there is a very similar problem in daily life, and there was a paper on that. So there was a paper suggested, like proposing to use machine learning technique to solve this kind of problem. So that is this. So assume you're in a room at night, and assume you want to take a photo of outside good scene. Because there is a window between you and the scene you want to take a photo, there is always a reflection from the window. So although you want to get a photo of this, what you get is this, the sum of the reflection plus the scene. So Li et al. Proposed to use machine learning technique, specifically generative adversarial network, to separate these two signals. So we found this, and we just thought, oh, it's really similar to our problem. We have an observed map where two emission signals are contaminated. So we want to use a very similar model to solve our problem in cosmology. So here is a result of the reconstruction of the large-scale structure at different distances with a generative adversarial network. So I show a video of how the reconstructed images changes across the whole training steps. So here is the mock observed data, which is composed true signal 1, true signal 2. And we input these observed images to reconstruct these two signals separately, individually. So at first, of course, the gun doesn't know anything about the signal, so it's almost random. But gradually, the machine learns how to separate signals, how these two signals at different distances different. And at the very end of the training, yes, it managed to separate two signals. For example, the key feature in this panel is like this kind of filamentary structure. This is quite well resolved, quite well provided in the reconstructed image of this. So we found that the GAN generative model is really useful for solving a problem. We have further applied the similar model GAN to our actual 3D data set we can get in the observation. 3D here means the image, 2D image, plus additional dimension of spectrum, like wavelengths, spectral. So there is a spectral direction additionally. So we actually have, as an observed data, we actually have this kind of 3D-dimensional data cube, which is composed two signals, hydrogen emission plus oxygen emission. Initially, at first, we have tried a very simple 3D CNN without changing any other architecture, but we found that it doesn't work that well, especially when noise exists. So in previous work of two-dimensional data, we didn't include any observational noise, telescope noise, for example. But when telescope noise exists. So under the very realistic situation, it didn't work. So we were wondering if we could improve the model by using our knowledge. When I say our knowledge, it is that we know the rest frame wavelengths of each emission lines. For example, H alpha has a rest frame wavelength around 5,000 angstrom and 6,000 angstrom, and this has a rest frame wavelength of 5,000 angstrom. So if we are observing at this wavelength, for example, this is composed of the H alpha hydrogen emission at redshift 1.5 and oxygen at redshift 2.2. Also, if we are observing at this wavelength, this is composed of emission, H alpha emission from redshift around 0.8 and the oxygen emission from redshift 1.5. So if we are observing this and this, there are two very similar structure traced by different emission, like hydrogen and oxygen. So we were wondering if we could use this information. So for this, we have developed kind of physics-informed architecture. Physics here means the rest frame wavelengths. How did we do that? So we just concatenated two data cubes, for example, here and here, where we know that there are two similar structures from very similar redshift ranges. And just concatenate these two data cubes and input them together to the base unit architecture. And output, so at the encoder is the same as the original design, but at the decoder we have two separate branches. One is for output in one specific signal, and the other is the other signal. So here is a result with our new architecture. So on the left, we show the input. In the middle, I show the reconstructed image in 3D. We can compare this with the ground truth. And you can see that although the input is really noisy because of the telescope noise we added, although the input is really noisy, the output reconstructed data is tracing very nicely the actual large-scale galaxy distribution. So it is same for this emission and this emission. So with this kind of physics-informed architecture, we nicely developed a very good model for resolving two or more emissions in observed data. So now we are planning to use this method in the upcoming observation targeting at very distant universe. So this was an example of machine learning application. And the second one, mock generation. Mock here means a data that mimics real observation. So when I say mock observation, it is kind of test observation that mimics real observation. So why do we need, we actually, in cosmology and astrophysics, we really need this kind of mock observation. Why? So one thing is to determine the observational strategy. So to determine how to scan the sky, or where in the universe, where in the sky to observe, or something like that. Or to test analysis pipeline. There are many analysis pipelines, so signal including the the one I showed, like signal separation, for example. So testing this, we need many different mocks. And of course, to compare our model theory and data, for example, including dark energy or like dark change in dark matter properties, we need mock data, mock like theoretically predicted data, and compare it with like observed data. And of course, for training the model I showed in the previous like slides, we need many different mocks, realistic mocks. The best way in astrophysics to create mock data is using simulation, more specifically cosmological simulation that traces the matter distribution in the very wide range of the very large area of the universe. There are mainly two types of simulation, cosmological simulation. One is the simulation with solving gravity between dark matter, like matter. So this is called dark matter only simulation. The other simulation is in addition to dark matter, we have baryonic, like baryons, which is, for example, gas or stars, dust, and so on. So it is basically, in addition to gravity, we need to solve the like hydrodynamics. So, and to form like to form stars or galaxies in simulation. Dark matter only simulation, because it's relatively like easier, it's really fast. However, there is no galaxies. We don't actually know where actually galaxies or stars form in the simulation box. On the other hand, this dark matter plus baryon one is adapt detailed galaxy formation computation. So we can directly get the, for example, positions of galaxies, information, properties of galaxy, and so on. However, it is computationally very expensive, so we cannot actually run this kind of simulation for many times for large volumes. So to create a mock data, a general approach is basically to adapt to use dark matter only simulation and just populate with some like simple scheme to populate galaxies in those simulations. And here is an example of the output of dark matter on simulation. The white colors shows the distribution of like dark matter, like matter in the universe. So you can see, for example, some kind of cluster of matter. Here is a zoom up of them. We call this kind of cloud of matter as halo, H-A-L-O. And because this is basically dark matter, we call it dark matter halo. Because we know that galaxies or stars are mostly in this kind of dark matter halo, the peak. So galaxies are formed in the peak positions of the dark matter distribution. A very simple approach is to put galaxies to the peak or the positions of the dark matter halo, assuming some kind of one-to-one relation between halo and galaxies. However, in reality, there are normally multiple galaxies in a single halo. And in the observation we are interested in, the multiple population, these kind of multiple population are really important. So what we want to do is to develop a method to populate multiple galaxies within a halo. And to do that, we need to take into account two things. First, properties of galaxies within a halo are correlated to each other. And second, existence of galaxies are very stochastic, so it's not deterministic. So for a given halo, depending on the situation or the timing we observe, there could be many galaxies, but in different situations, they could be, even though the properties of a halo, dark matter halo is completely the same, they could be very different properties of galaxies, number of galaxies. So it's not deterministic. To take into account this kind of thing, we thought of, okay, we can use kind of generative model. So again, we want to model the conditional probability density, P, L, blah, 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 L, for a given M. So here, Li means the property of ice galaxy. And M here means the property of dark matter halo. So the number of galaxy N here differs for each halo. So we thought that training with a full n-dimensional data, for example, this can be done with diffusion model or any other generative model, but doing this is wasteful, especially when there is only a small number of galaxies than the whole large N galaxies. So we thought of using autoregressive generation. And this could be very efficient. So autoregressive generation means that for example, for two galaxy cases, to model this conditional probability density, we divide them into two components. One is this, and the other is this. So first one is only obtained from the condition, and the second component is like modeled condition on the first galaxy and the dark matter halo, that condition. So this kind of scheme is actually adopted in recent large language models, and we just thought it is quite useful. So as a quick recap, in large language models, the autoregressive generation is something like this. So when we input some kind of initial word, I, for example, the model predict the probability density, probability distribution of the words. For example, can could be 30%, blah, 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 blah. And from the modeled probability, the model samples a single word, for example, and they just continue this process, blah, 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 blah. And at the end, when kind of end token is sampled, the generation stops automatically. So this can be used for our like generative model. We developed a very similar model as the LLM, and we named it Cosmogrid, which is now available in GitHub. So we first input the condition, the properties of halo, and the model first predict the probability density of the properties of the first galaxy. And then they sample a single property. Then from these two input, they model the probability density of the second galaxy. They continue, and when generation, like when the luminosity or the property of the galaxy sampled is very small, or luminosity is very small, or only the very faint galaxy is sampled, the generation automatically stops. By doing this, the number of galaxies are automatically determined. And we trained this model with cosmological hydrodynamic simulation. And here is the result of learned probability density. So these two show the two very similar dark matter halo. One has a number m equals to this, and the other is number m equals to this. These two numbers are very similar. Although this halo mass, which is properties of most important properties of halo, are very similar. The distribution, predicted distribution of, especially for second and third galaxies, are quite different for these two. So here, blue is the predicted probability distribution for first galaxy, and light blue is second, orange is the third, and so on. So with this autoregressive modeling, we have managed to model very complicated galaxy distribution in a halo. Here is the result of the number of galaxy per halo. So for the generated, the solid line shows the generated one, and shaded region is this is another cosmological hydrodynamic simulation, which is considered as a ground truth. So we can achieve a very good consistency between ground truth and our reproduction. And our model can generate a variety of number of galaxies per a halo. And also, as I mentioned earlier, the correlation between galaxies in a halo is quite important. We have shown that as an example, the first galaxy and second galaxy correlation are very good in good agreement with the ground truth. So using this model, we have created the mock data. So this red region is not the region where is not used as a training data. So you can see overall the reconstructed image on the right is quite similar to the image on the left, which is ground truth. And importantly, generating a lot of galaxies, like 800,000 galaxies in a very large volume, is quite fast, only 20 seconds. And for reference, generating ground truth data with hydrodynamic simulation takes a few months on supercomputer. So it is quite good speed up. We have also checked statistical properties are also good in good agreement. And also compared to the previous method, our method is much better. I don't go into detail because the time is not time is limited, but we have found that our model is really useful for making some prediction for actual observation. And now we have generated a very large mock data, which is almost impossible to create with cosmological hydrodynamic simulation because it is costly. And it looks like this. And now we started applying some kind of test observational pipeline of the upcoming observation to the generated mock data of this. So here's a summary. In cosmology, measuring the large-scale structure or large-scale galaxy diffusion is crucial. And for this, we have used machine learning techniques for two different topics. One is separation of contaminated emission lines. We used a generative adversarial network to separate different large-scale structure signals. And also for creating mock data, we have used old regressive generation model. And we have found that it can actually efficiently populate galaxies, and it is really fast. So these machine learning techniques are really important for us to appropriately and efficiently handle the enormous volumes of data that will emerge in the upcoming cosmological surveys. So that's all from me. Thank you very much for listening.
Hey, thank you very much, Moriwaki sensei. Okay, time for questions.
May I ask?
Okay. Yes, please, yes.
So about the separation of, by the way, thank you, great talk. Separation of the foreground and the background. I didn't understand what was the ground truth in there that was used to train. Like, how did we separate it in the first place?
Thank you very much. Actually, this is also simulation, like the simulation I mentioned in later slides. So these ground truths to train the model is created from realistic simulation. So it's not actual observation because we need, in any case, a ground truth, which we cannot get from actual observation. But simulation is really consistent. We have checked, and many people have checked that simulation is really consistent with actual observations, like actual universe. So we kind of believe that simulation is reflecting what we actually observe in.
I see. And how does the separation work in the actual large scale structure, like how when you made the whole map, like how do people separate in that setting? And is the fact that one of them is oxygen and the other one is hydrogen important to do the
Ah,
separation?
yes, thank you very much. For the first question, it is actually like very or recent observation. It's ongoing now, and we haven't get actual like observed data like this. We will get this kind of data very soon, like in a few years. So we are planning to apply this method in near future. So for the second one, oxygen. So why we focus on only two line, oxygen and hydrogen, is that these two are the most like the strongest at this wavelength regime. So for example, here you can see this is most the strongest. This is H alpha, the one I mentioned. And although in this specific case, the one I mentioned, O3, oxygen emission, is here, it's not that strong in this specific case. But we know actually that in some different cases, maybe I should have shown different example. But anyway, in most cases, this oxygen line is also very strong. So basically these two, considering these two are almost enough. So that's why we considered these two. But of course, we can think of using multiple lines in practice.
Mhm. Thank you.
Thank you very much.
Okay, some more questions. So please feel free to speak up or raise your hand, either way.
I think there is a chat, but
Okay.
I
There's a
somehow
chat.
I can't
Mhm.
check. Okay, large scale structure of galaxy distribution seems bubble shape. Oh, how about surface tension? Research in gravitational equation. Oh,
Mm.
this interesting. Yes, as you mentioned, it is called kind of bubble-like structure. So yes, this kind of shape, right? Yes. Let's go structure galaxy. Yes, how about surface tension research? I'm not that familiar with this kind of topic. Yoshi doesn't have any comment.
It's pure gravity. It's only what's it? Inyoku. What's it? I forgot the word for it's only Inyoku. But curiously, only by gravity we can see this the formation of this kind of structure of like a bubble shape. So this is interesting topology indeed.
Yes, true. So, yeah, thanks. Now it is clear to me. Yes, no tension, but interestingly.
Yeah,
Yes.
thank you for the question. Either like in typing in the chat or speaking up or raise your hands and so on. Either way. Anybody? Okay. Okay, time is already in and lunchtime, so let's close this seminar. Thank you, Moriwaki-san, again, and thank you for joining today's seminar. Thank you very much to everyone. Thank you.
Thank you.